later, what I was babbling about was, for the quiz, try to find an antiderivative for each of these. Once you clean it up, you may be able to, you may not. Give it a shot. And then back home, there is a physics survey that I need everyone to take sometime today. And just want some information about what you remember about physics, if anything, if you even ever had any physics. So we might need my math lab later. All right, let's do a surface area. So surface area of cones, actually, it's kind of a little pain to set it up algebraically, but the formula ends up being relatively simple. You end up with this average radius that you revolve through, and then you just need to know the slant length of the object. And the slant length comes from the Pythagorean theorem. So surface areas, let's call them SA, with respect to x, would be something like from an A to a B, 2 pi y. That would be our average radius as we're cutting through. And then the slant length comes from the Pythagorean theorem, which is 1 plus f prime of x squared inside the square root. And we did a little algebra a couple of days ago showing that that's the calculus version of the Pythagorean theorem. And y here is likely to be a function of x because we are integrating with respect to x there. And then there's a similar formula if we're revolving around the y-axis. So here, again, this would be revolving about the x-axis. So we're going to apply that. The function we're going to take a look at is y equals 1/3 x cubed. And we are going to look at that on the interval from 0 to 2. And based on the formula above, we are going to go about the x-axis. Similar to the arc length problems we did in the previous section, it's a good idea to kind of slowly build the integrand up there. And so my recommendation is to start by taking f prime. Now, oops, missing a parentheses right there. Before I do that, what should I do? I should draw this, yeah. So either whip out a calculator or start sketching this. Let's see, from 0 to 2, this is going to be all positive. There's 1, there's 2. If I cube 2, I get 8, but I'm taking 1/3 of that. 3 goes into 8, 2 2/3 times. So if that's 2 there, I'm going to have to go up 1, 2, 3 here. And then my curve is going to have the point 0, 0, 1, 1/3, maybe about there. And then 2, 2 2/3, so maybe about right there. So this is the curve that I am going to revolve around the x-axis. And then that's going to give me a funky cone shape. Something like that. And what we want to know is how much paint is it going to take to go around the outside of this cone? That's surface area. All right, let's do it. So our procedure says first find y prime. Y prime is going to be 1/3 times the derivative of x cubed, which is 3x squared, which cleans up nicely to be just x squared. Then, oops, I'm going to switch color. Then we are going to square that. That's just x to the 4th, and add 1. So 1 plus x to the 4th, oops, x to the 4th. And then we stick it in a square root. And not much happens good here. Now I'm stuck with 1 plus x to the 4th inside of the roots. That doesn't expand very well unless you use complex numbers. We don't want to go there. And so now I'm going to build my integral here. So I'm going to have the integral. We were going x equals 0 to 2 of 2 pi times my function. The original function is 1/3 x cubed times this square root. So then I think, okay, can I come up with an antiderivative? Now I'm thinking back to chapter 5 when we did those substitutions, and I know the derivative of x to the 4th is a version of x cubed, so that makes me happy. So I think a u substitution might work here. What should we choose for u? The whole radicand here? Yeah, so if we let u equal 1 plus x to the 4th, oops, my pen freaked out. Try again, 1 plus x to the 4th, then that implies that du is equal to 4 x to the 3rd dx. Now I don't have that 4, but I could throw it to the other side. So instead of a 4 on this side, I could say it's going to be a 1/4 du right there. So I'm going to replace my x cubed dx with a 4 du. And then the 1 plus x to the 4th is a u. So that gets all the x's out. And that's the goal. When we do a substitution, we got to eliminate all x's, and they got to be u's instead. And it looks like I can totally do that. So let's rewrite that on another page here. So it looks like we have the integral, I'm going to ignore the boundaries for the moment, of 2 pi 1/3 square root of u, and then I'm going to have a 1/4 du in place of the x cubed dx. Did I miss anything? 2 pi 1/3, nope, that looks like everything there. So just cleaning this up, we could at this point replace u x boundaries with u boundaries. So for example, back here, focusing on this, if x is 0, u would be 1, right? So I could let u go from 1 to, and if x is 2, let's see, 2 to the 4th is 16, plus 1 is 17. So I could let u be 17, and then I don't have to worry about a reverse substitution, which works out okay here. All right, so pulling some stuff out, 2 times a 4th is a half. Half times a 3rd is a 6th. So I have a pi over 6 on the outside. Integrating as u goes from 1 to 17 of, I'm going to write it as u to the 1/2 du. And then what's an antiderivative here? U to the 3/2 when we add 1 to that. And then we're supposed to divide by 3/2, which is the same thing as times 2/3. So that's an antiderivative. The pi over 6, we can just leave that chilling out front. And then we have to evaluate this from 1 to 17. Okay. So evaluating, pi over 6 is out front. I might as well bring the 2/3 out front too. And then I've got u, which is 17 to the 3/2 minus 1 to the 3/2. 17 to the 3/2, not much I can do there. The 2 and the 6 will divide, so it looks like what? Pi over 9? And I don't think we can do any better than that right there. I kind of like the 17 to the 3/2. One alternative there, if I scribble off to the side, 3/2 is 1 1/2, right? So 17 to the 3/2 is the same as 17 to the 1½ which means it is 17 times 17 to the 1/2, right? 1 plus 1/2, which is 17 square roots of 17. So I could rewrite that as that. Does that help any? No, not really. This one, I think, uses slightly less ink if we weighed the two of them. Usually I think simplified means it uses less ink. So I think I like this one better today. Maybe tomorrow I'll like that one better. And then we should do a numerical approximation. So I'm going to do that in two different ways. I'm going to type that into my calculator, and then I'm going to type my integrand into something like GeoGebra and get an approximation. So doing that, first, let's take the pi over 9 times parentheses 17 raised to the parentheses 3 over 2, right? Close the power, -1, close the product. And my calculator says it's about 24.12-ish, okay, for an approximation. So if I go to the nearest hundredths, so this is just a side note, if you like square roots better, oops, wavy equals approximately 24.12. Now, provided I set up the integrand correctly, GeoGebra can give me an approximation too. I'm sure MathWay can also. Where's GeoGebra? There we go. Start new. And so I start typing int, and then I like the third version here. So I want the integral of 2 times pi. Let's see what else is in there. Times 1/3 times x to the third times the SQRT of 1 plus x raised to the 4th. That's my integrand. And then I'm starting at 0 and going to 2. And it's going to draw a picture. The picture is not all that meaningful. What is meaningful to me is the value, oops, move 24.12. And let's blow up the fonts, options, font size, 28. Okay, so GeoGebra is giving me the same value that I calculated by finding an antiderivative. Sometimes we're not going to be able to find an antiderivative. So let's try another one. Okay, this time let's take a look at y equals the cosine of x. And let's try the interval from 0 to pi over 4. And again, we are going to go about the x-axis. So let's do a quick sketch of that. Let's see, cosine goes up to 1. If I say, let's see, pi over 4, pi over 3 is close to 1. So if that's 1, pi over 4 is going to be about here, I think. And let's see, if that's pi over 4, pi over 2 is going to be somewhere over here. And I know the cosine peaks here and bottom or hits its midline right there. So this curve comes through something like that. And I want the chunk between these 2 points. So let's pick a different color. Red. So it's this chunk here that I'm going to revolve about the x-axis. So drawing that to the best of my ability, I'm going to get a bigger circle out there and a slightly smaller circle over here, and it's going to curve slightly over. And let's say that's kind of inside. Dotted line, a little bit of shading here. All right. Maybe shade this in here like that. Okay, that's my best artistic rendering of the shape we're about to generate, and we're trying to figure out how much paint this would take on the outside, essentially. All right, so now we have to start setting stuff up. So y prime, derivative of cosine is the negative sine of x, is that right? And since we're going to be going back and forth between derivatives and antiderivatives, we always got to double check in our brains. Ooh, did I go the right direction there? Y prime squared is the sine squared. Negative times a negative is a positive. Then we're going to have 1 plus that. And immediately what pops into my brain there is, ooh, is that the Pythagorean identity? Not quite. Just remember the Pythagorean identity says if you have the sine squared of x plus the cosine squared of x, then you get 1. Solving for the cosine, that would be 1 minus the sine squared. It's like, oh man, so close, but not quite there. Okay. There is, actually, I don't know, does anybody remember this one? There is a formula for cosine squared of x minus the sine squared of x. Anybody remember seeing that one before in their identities?
Isn't that the Pythagorean identity?
The top one is the Pythagorean identity. The second one is not.
Oh.
Because it's got a minus in the middle. I'm pretty sure this one right here is the cosine of 2x. Which doesn't help me here either. So I'm just kind of brainstorming identities, because in a second, right, what are we going to have next? We're going to have the square root of that. And this is where life gets interesting. Oops, I wrote that in the wrong spot. Let's move you over. You go there. All right, so now I'm ready to stick it in the whole integral and see if anything nice happens. So my surface area is going to be equal to the integral as x goes from 0 to pi over 4 of 2 times pi times the original function, because that's our radius. That was what, the cosine of x. And then I have the square root of 1 plus the sine squared of x dx. And this kind of looks maybe promising, because the derivative of the sine is the cosine, but the square here is kind of a problem. So for example, if I say, let's try u equals 1 plus sine squared, then du would be what? 2 sine of x times the derivative of the sine, which is the cosine of x, dx. And I'm excited about seeing the cosine, but I'm not happy about seeing that sign there. That doesn't make me happy. So like, oh man, not gonna work. You know, I could try to divide the sign to the other side, but then I'll be mixing up my u's and my x's. Bad, not a good idea. Don't do that. So then I'll say, okay, what? Ooh, somebody's got an idea. What is it?
Try solving the Pythagorean identity for sine squared of x and then plugging that in.
Yeah, that's a good idea. So if we solve Pythagorean identity for the sine squared, that's going to give us that the sine squared is 1 minus the cosine squared. And if we replace in there, we would have 1 plus this, which is 1 minus the cosine squared of x, which gives us 2 minus the cosine squared of x, which leaves us slightly worse off, I think, if you consider 2 to be more of a problem than 1 there. So that didn't help. Something I thought of, remember we used the half angle, double angle formula the other day in class? Maybe that would be helpful here. So at this point, I'm whipping out a sheet of trig identities and praying I find something that's helpful. So let's try trig identities. According to Google, lots of people search for this regularly because it just popped right up. And you think I went to SOS Math the other day. All right, so we got the Pythagorean identity. So far, that didn't seem useful. Co-function identities, maybe, maybe not, swapping sines and cosines, but then we have to change the inside, which a U substitution could help with. Some difference. Okay, double angle formula. So here's, I thought the double angle formula might be hopefully either up here or down here. Now here it says the sine squared can be replaced with 1 minus the cosine of 2u. That gets rid of the square. That might be helpful. Let's try it. So we're going to replace the sine squared with that and see what happens. Okay, so what is it? It says 1 minus the cosine. So new page. We're trying to deal with 1 plus the sine squared. And we just saw an identity that says the sine squared is 1 minus the cosine of 2x all over 2. And I have a 1 plus right out front there. So let's see, cleaning that up, that's what? 1 plus 1/2 minus 1/2 cosine of 2x. 1 and 1/2 is 3/2 minus 1/2 cosine of 2x. So this is really nice because now I've gotten rid of the square. So maybe this would make a good u. Let's try it. So if we let that be u, you're also going to get way better at trig this quarter. So if we say that's u, then du, well, that goes away, is going to be negative 1/2 times the, let's see, the derivative of the cosine is what? Negative sine of 2x times the derivative of 2x, which is 2. Ooh, that's beautiful. That's just the sine of 2x. Dx. Oh, darn it. Although that's a nice du, are there any sines of 2x hanging out up there? Okay, well, hey, there's a formula for the sine of 2x. Let's take a look at that. That might help. So back here, it says the sine of 2x is twice the sine of x cosine of x. Oh, wait a minute, that looks familiar. Where did we see that before? Ah, oh, no, not there. Not there. Oh, there it is. That was my du from before. Ah. So if I try the identity, the most obvious identity, it takes me back to the failed substitution we had earlier. So at the moment, I'm like, I don't got anything else up my sleeve. What are we going to do? Any thoughts? Kind of give up. We're just going to have to say, I don't think we have any techniques to find an antiderivative right now. So we have to resort to GeoGebra or Wolfram Alpha. Now, some programs actually will come up with an antiderivative. And then you look at that and say, oh, I think I can figure that out, how to get there. So let's cheat and try, let's see, Samantha recommended MathWay. And so to use MathWay, I think she said, push this button here. No, push this button here. Ah, calculus. Okay. And there's an integral button here. All right. And we want to, let's see, the constants aren't really a big deal. The other stuff is. So if I just type, let's see, what was it? There was the cosine of x on the outside, and then the square root of 1 plus sine squared. And I don't really care about the constant. She said I don't need to do it dx. So I'm not going to plug in boundaries. I'm wondering if this can do a definite integral. So I'm just going to hit this button and see what happens. I've never used this program. Ooh, and it says I don't know what to do with that. How about find the integral? Okay. And it says, sorry, we can't help you here. So I could plug in my constants and my boundaries, and then maybe it could help. I'm going to go to Wolfram Alpha, see if it can help. So I got to type the same thing here. Now, Wolfram Alpha, I have to type the word integral, and it's kind of like typing in GeoGebra. So then I would type, let's see, cosine of x. Sometimes I'm careful about typing times. What's next? Square root of 1 plus the sine squared of x, close the square root, close the integral, and hope it understands what I mean if I typed it right. Enter. And it's computing. Oh, and it has an antiderivative. Okay, so it looks like that's typed right, doesn't it? Let's blow this up. Oh, this is exciting. What is that? SINH to the -1? That's called the inverse sinh. It is, that's what it's called. Anyone ever seen that before? You have? Where have you seen the sinh? Yeah, it's called a hyperbolic sine. But notice it's got a sine inside of it. Ooh, so just a quick note on the inverse sinh. The sinh function, which we'll talk about later in the course, new page. So sine h of x, it's pronounced sinh, is equal to, let's see here, I get this right, I believe it's e to the x plus e to the -x over 2, if I remember right. I better look that up just to make sure. It could be a minus in between. So Wolfram alpha, let's get a new page. SINH. Oh, I'll just type SINH. And it says, yeah, hyperbolic function. Wikipedia is usually a good place. Wikipedia math is usually awesome. I know people put Wikipedia down for a lot of things, but it's pretty good. And further down, I think they'll give us a better, so they're kind of giving a geometric explanation of it here, which is kind of wild. I just want to go to the standard analytic expressions. Oh, it's a minus in between. Okay, so it's the cosine. The hyperbolic cosine has the plus in between. And my eraser is missing, of course. So who cares about these hyperbolic sines and cosines? Well, it turns out these things have properties like the sine and the cosine. So for example, suppose we took the derivative of that with respect to x. E to the x minus e to the -x over 2. Well, the divide by 2, that's just a constant. So I can safely ignore that. So that's just going to hang out. Derivative of e to the x is e to the x, right? What's the derivative of e to the -x? Negative e to the x, right? Negative e to the -x. With the negative out front, that's going to give me a plus e to the -x. And it turns out this right here is the definition of the hyperbolic cosine, which is, I think, pronounced cosh. Well, that's pretty clear it pronounced cosh, right? The sinh one I always thought was weird. Why sinh? There's no C in there. That's the cosh function. So with regular trig functions, derivative of sine is cosine. Hyperbolic trig, derivative of the hyperbolic sine is the hyperbolic cosine. Yeah. And it turns out the derivative of the hyperbolic cosine is going to be the opposite of the hyperbolic sine. Where did they come up? Well, has anybody lost any power or phone service recently this year? Nobody here has? Okay, my friend has, who lives upriver, and I think too much ice got on the line and the line snapped. Okay, well, have you ever noticed that, oops, if you have a telephone pole and there's a wire, does the wire stretch straight across in between them? No, that wire is going to have some sag to it. If they try to stretch it completely straight, it will snap because gravity is pulling on that uniformly. And it turns out, this is a physics problem that can be solved, it's pretty hard, but it's doable, that the equation that gravity causes this thing to have the shape of is a hyperbolic sine or cosine. It's one of these guys up here. Yeah. So this is likely some version of the sinh function. Just like with a parabola comes from a quadratic equation. The name of the shape is parabola. The name of the shape that gravity causes chains and chords to settle into is called a catenary. Is the shape of the curve. Okay, so if you graph a hyperbolic sine or cosine, we call that shape a catenary. Some people call it a catenary, however you want to pronounce it. But that's the shape. So we'll take a closer look at those later. Did you guys look at these derivatives back in Calc 1? Did it come up? Okay, so we'll talk a little about them, I think, in chapter 7 or 8. It occurs. So at the moment, we haven't really studied hyperbolic sines and cosines, so we don't have the tools to justify Wolfram alpha's solution here yet. We need some more techniques to kind of mess with it. So it turns out there is an antiderivative, it's just beyond us at the moment, right? So with these problems, you got to remember, do your best to simplify it, see if you can guess at an antiderivative, playing around with a substitution perhaps. If it doesn't work in a couple, 3 tries, then plug it into GeoGebra. Okay. If you jump right to Wolfram alpha will often give you an antiderivative, but if it's complicated, it will often be in functions you've never heard of before. Right? Like for example, consider the function relatively simple. If I take the sine of x and I divide by x. Sine of x, and you've looked at the limit of that before, right? As x goes to 0, this goes to 1. But what happens if you try to take the integral of it? Is there an antiderivative? And if we ask Wolfram alpha is going to say, yeah, the antiderivative is the SI function. Oh, what's the SI function? Well, I'll show you what the SI function is. The capital SI, there's a lowercase SI function too, so let's not confuse them, be case sensitive, of x, is the integral as t goes from 0 to x of the sine of t over t dt. Wait a minute, that's what I was just trying to take the integral of. So the sine function, it's the psi function, its definition is the integral we were trying to evaluate. Guess what that means? There is no fundamental antiderivative for it in terms of functions we've ever seen. Okay. There are ways to handle it besides just calling it SI. We look at that in Calc 3. But it's just there's tons of functions out there that we have no fundamental antiderivative for based on simple functions that we know now. Things that we see. I mean, sine of t over t doesn't seem that complicated, but we don't have an antiderivative for it. Okay. And how do you know if there's no antiderivative? You try a few times, and then you keep learning more math, and pray some year you figure it out. And we've been accumulating these over the last couple hundred years. Can we answer every question with respect to an integral? No, but we can answer most that people ask these days by either saying, yes, there is a fundamental antiderivative, or no, we've just created a new function. Okay. So, all right, back to the task at hand, modules. Let's look back at this quiz. So here you're going to attempt to take the tangent function as your curve in the quiz, and just like we did with the cosine, hope that it might clean up a little bit. Something that might help there is, let's see, what's the derivative of this tangent? Secant squared. So we're going to have a 1 plus secant squared secant to the 4th. But there are some identities that might help there. So this may be one that you can, considering Pythagorean identities. Secant squared is 1 plus tangent squared. So it may work out that you can find a u substitution using some trig identity, but it may turn out like the cosine, it's beyond us at the moment. Give it a try, see what happens. Worst case scenario, you try a couple of substitutions, a couple of trig identities, and then you go to Wolfram alpha and plug it in. Right. So that's what we have to do here for this function. I have to go to integral, oops, third option, and then type my function carefully. So my function was 2 pi, what was next? I'm going to put some multiplications in. Those are making me nervous sitting next to each other. Cosine of x times the sqrt of 1 plus sine squared of x. And I think I'm done with that. And we were going from what, 0 to pi over 4? And GeoGebra says it's about 4.79. And we have to settle for that since we don't have a technique to come up with. Let's hide that other one. We don't have a technique to come up with what Wolfram claims the antiderivative was. Let's see, let's go back to my other one. But Wolfram alpha can also do definite integrals by just typing comma and then giving it the boundaries. 0, comma, pi over 4, close parentheses, enter. And if you typed it right, Wolfram alpha will try to do pretty print here. Oops, I'm missing some things. I'm missing my constants, right? What were my constants? 2 pi? All I had, right? And we better put a time so it doesn't get confused. Enter. And there's the 4.79-ish there. It's also trying to give it to me in terms of the antiderivative it came up with involving the hyperbolic sine. And again, I think in chapter 8, we'll probably be able to figure this out, why that is the case later. All right, so you guys are so lucky. There was no technology like this when I was taking calculus, and it was just, we couldn't even, in most cases, come up with an approximate answer, because there weren't computers easily accessible that would do it for us, unless we went to see the computer science department and said, hey, can you help us come up with an approximation based on a Riemann sum? And then somebody would type that up. But you know, it's much harder. Now we have all this amazing technology. All right, so I think that's pretty good on that right now. I'm gonna do a quick introduction to part of the physics that we're gonna go over. And we are, I think, as of yesterday, officially a day and a half behind, possibly 2 days behind. I may decide next week to skip section 6. I'm gonna rewrite this calendar and see how it looks for the rest of the term. But my plan now is 6.6 is a maybe. I'm only gonna cover half of chapter 7. I said I was gonna cover all of it in the syllabus. I'm only gonna do half of it because chapter 8 is the next most important thing we need to cover. And that has all the weird techniques to deal with things like hyperbolic sines and like we don't know how to take the antiderivative of the square root of 1 plus x squared yet. We haven't figured that out yet. So that's something we'll learn in chapter 8. The next, oh, good question. So the next test is just going to be chapter 6, and I meant to have it done today, a sample test of the kinds of questions I'm going to ask on that. So there's probably the end of next week, we'll have a chapter 6 test. And because these problems are so complicated, it'll be part take home. So about half of the questions will be take home, half of the questions will be in class. Because the setup on them and the algebra is so crazy, you really need time to think about it. And a 50-minute period is not necessarily a good venue for that. Okay, so a little bit of physics. The kinds of things that we're going to look at in section 6.5. And don't forget, sometime today, take that physics survey I put in the Canvas course there. It takes you out to it's a Google form. It's embedded in the course. And then Google will email me your results. So a couple things to consider. Idea of force. Okay, so we all have the idea of force. Somebody pushes us, we drop something. If I jump off a desk, there's the force of my landing, okay? The standard physics definition is force is mass times acceleration. And the most basic one is acceleration due to gravity. And depending what your measurement system is in like feet and seconds, I think it's around 32 feet per second squared. In meters and seconds, it's about 9.8 or 10 meters per second squared. And the key about gravity is an acceleration. So people have known about gravity for a long time, right? They hypothesize, oh, why aren't we just floating away? How come we can't be like birds? Or and at first they thought gravity changes your position, which it does, right? If I get on top of the table and I jump off, my position changes. But it wasn't to the time of about Galileo that people realized it doesn't just change your position, it changes your speed. Otherwise, it wouldn't matter whether I jumped off the table or jumped off the roof if it only changes my position. But it actually changes my speed. And if you think about a change in speed over time, right? Speed is usually something like meters per second or miles per hour. So in units, what this gives me is something like meters per second per second. And that's why you'll often see acceleration written as something like meters per second squared, or maybe miles per hour squared. And it sounds weird. How can you square an hour or square a second? I mean, I can see squaring a foot. But when you look at it in this instance here, it's just change in speed. How does speed change? Well, it changes over time, just like distance does. Okay, so that's where we get the units there. Other things to consider about force. You have to have a change in speed to cause a force to happen. Like when you feel yourself hit the ground after a jump, right? I had a speed, it then turned to 0. That's acceleration, or in that case, deceleration instantly. And that's where the idea of force comes from. Other things to think about. I can hit something or push something, and if I keep doing that, I'm straining my muscles. I'm using energy, right? And that's what we call work. And work is defined as force times distance. Force times distance. And if it's a constant force, no big deal. That's just a simple multiplication problem. But if it's a variable force, if that force changes, then we have to use calculus. So this is only if force is constant. Let me do it on time. Get a couple minutes, good. If force varies, then we have to do it different. So suppose we have a variable force. We're going to call that capital F of x. Well, if capital F of x is measured this way, and I let distance be measured that way, let's suppose it's just a straight line like that. So the farther I try to move the thing, the harder it is to move. A situation that this happens is a spring, right? Take a spring, a tough spring. The first centimeter is not too bad, but if you try to go 5 centimeters, like, oh, I'm not strong enough to move it 5 centimeters, because you need more force to move it farther, because you're trying to take it out of its equilibrium state. So you get a situation kind of like this. And if you look at, say, the area under this curve, well, that is your variable force by your distance. That's the idea of integration, isn't it? In terms of an area. And that's supposed to be an A there, area. And so that means this area is actually a calculation of the work done. So if the force varies, then this equation right here turns into the integral as x, my distance, goes from someplace A to someplace B of my force function with respect to x. Okay? So with a variable force, we need calculus to calculate it. Classic example that we'll do next class, we don't have time today, is trying to pull or compress a spring. Okay. Old scales used to work on springs. There was a system of springs inside in some way. That spring could be a curly spring like we're familiar with, or it could be an arched piece of metal that can also work as a spring. If you ever looked under a truck, we still have those in trucks. So there's a couple of ways we can design a spring. And springs tend to have like a constant way they can be stretched, which leads to a situation like this. Other thing to consider before we go away is the idea of weight versus mass. Okay, so kilograms is a unit of mass. It's how much stuff is in me. Okay, now some parts of me are more dense than others, like my bones are more dense than my blood vessels or my blood. Okay, so I have variable density, but I have all of this stuff in me, and it doesn't matter whether you put me on the moon or Mars or here, I have the same stuff. Weight is when we take, that's a force. That's when we take our mass, like kilograms, and we multiply by acceleration, like gravity. And if we're using the metric system, the classic unit of weight is called a Newton, N. And a Newton is mass, kilogram, for example, times acceleration. Standard unit of acceleration in the metric system is usually meters per second squared. So weight has a weird unit set. In the case of the metric system, it's kilograms times meters per second squared. Does anybody know what pounds is? Is pounds a measurement of weight or is pounds a measurement of mass?
Both.
Boboth?
Because
No.
American system is stupid.
No, it's not. It's actually not both. Although we call it mass sometimes. It's because you've probably heard the classic example. You're lighter on the moon. You will weigh less pounds. Yeah, pounds is actually a unit of weight, not mass. So that means pounds is some mass unit times acceleration. And my recollection is the imperial measurement for mass is slugs. So I would have the same amount of slug mass on Earth as I would on the moon. Okay, so that's another idea we have to keep separate as we work through some of this stuff. So we're going to play around. Next class, we'll play around with mass, weight, force, work, and then we'll also get into pressure, like underwater. Okay, and that's what section 5 is all about. All right, so I'm going to go into my math lab and change some dates in there. I haven't posted the my math lab section 6.6 homework because I'm not sure if we're going to cover it yet. I posted that quiz for section 4, surface areas. If you haven't tried it yet, please give that a try. And otherwise, just be safe out there in this crazy weather. And I'll see you all next week or tomorrow if anybody wants to come study calculus with me. I'm not going to cover anything new tomorrow. It's just stuff we've been doing. So any kind of question you have, feel free to stop by. And